so this is our Honors Chemistry Section 8.3 lesson video, Part 3. Now, I probably really need to make 4 parts, but I just really want to finish, so this video may be super long. But that's okay. So if you haven't watched the first 2 parts, make sure you go back and watch those because I go over all the different VSEPR shapes for electron domain geometry and molecular geometry. If you did watch it, I know you probably lost sleep over whether did I ever find that T-shaped molecule that I was missing, and the good news is yes, I did find it. So thank you for worrying about that. I'm sure you were just incredibly worried about it like I was. So I found my T-shaped molecule, so we're good to go. All right, so let's go ahead and get started. So what I have is a bunch of different molecules, and we're going to draw the Lewis dot structure. And then based on the non-bonding and bonding pairs, we are going to determine I know it asks for the molecular geometry, but we're going to go ahead and do electron domain and molecular geometry. We're going to go ahead and do both of them for all of them. All right, so the first step is we've got to draw the Lewis dot structures. Now I'm going to start doing this part quicker because you should have learned how to do this in the 8.2 sections. We don't have time to keep going through, but these are the steps that I'm going through. So if you're still having trouble with Lewis dot structure, go back and watch 8.2 videos because mainly in this video to help with the speed of things, I want to focus more on the VSEPR shapes, not the drawing of the Lewis dot structure. But I'll still go over it. All right, step 1 is add our valence. So oxygen has 6 times 3, that's 18 valence electrons. Now normally you are not going to know the shape of a molecule before you start unless you have it memorized. So just start by drawing everything flat. That's the easiest way to do it. Okay, so I'm going to single bond everything. And then I'm going to make everybody stable. So this O needs 6 more. This O needs 4 more because it has 4 from the bond. And this O needs 2 more. So see, this is what I mean by we're going to start going a little faster on the Lewis dot structure part. I'm allowed to have 18. I have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. I have 2 extra. I need another bond. I have 2 options of where I can put the bonds, so automatically I know I'm going to have resonance. Once I add my extra bond, I'm going to adjust for my octet. So 2, 4, 6, 8, 10, so I remove 2. 2, 4, 6, 8, 10, so I remove 2. So this is the structure that I end up with. Now, of course, I also know I need resonance, but because I'm going to have to draw it in the proper shape anyway, I'll wait and draw my resonance then. So see, right now I have it drawn as a straight line, but the problem is we have this lone pair right here. That lone pair is going to keep it from being linear. It won't be linear because that lone pair is going to cause it to bend downward. So when I actually draw it, I need to draw this shape, not linear. All right, so let me do that first. However, I can at least draw it 2D because if you look, my bent can be drawn 2D. I don't have any pointing towards y'all or coming back to the board. Okay, so once I draw it, I'm just going to bend my bonds downward. And then whenever I'm drawing 3D shapes, I kind of like to balloon out my lone pair just to remind myself that it takes up space. But I also have to include my resonance because the double bond could have gone on this side. And so notice the single bond oxygen always has 6 valence electrons, or not lone pairs, lone electrons, and the double bonded one has 4 lone electrons, and I keep that bubbled up lone pair. So we need to do the electron domain geometry and the molecular geometry. So I like to abbreviate electron domain as E negative and D for domain, and molecular is M/C. All right, so remember, molecular geometry assumes we cannot see the lone pair. So it's just going to look like this. So my molecular geometry is called bent. However, for electron domain, we can see there are 3 domains. It doesn't matter whether we would visually be able to see them or not. So that is based off of this right here. See, 3 domains. It doesn't matter whether they're bonding or non-bonding when we're talking about electron domain geometry. So 3 domains ends up being trigonal planar. And so you can see how you have your 3 domains But because the top one's not a bond, is not a bonded atom, that's why it ends up being this. But because we have the 3 domains, it's still 3 like a triangle in the same plane. All right, so let's look at our next one. We have SnCl negative, Cl3 negative. So don't forget that little negative there. So Sn has 4 valence electrons, Cl has 7 times 3, and then I have 1 extra one because of that negative charge. So we have 21 plus 5, which is 26. So I'm going to single bond everybody. Sn is going to go in the middle. And so again, for right now, I'm just going to draw it flat. I got to make everybody stable. So right now, my Cl needs 6 more each. Because we're just trying to get everybody to have 8. And then Sn has 2, 4, 6, so it needs 2 more. So now everybody's good and stable. So now I check my total. I'm allowed 26. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. Boy, that worked out well. So last step is I have a charge. So I am going to have to bracket it, but I have to redraw this anyway because I have to put it in 3D form. So I'm going to wait and bracket it then. Just like how I waited to do my resonance structures when I drew it 3D. So if you look, I have 4 domains. So here, let me balloon out my lone pair so you remember that it actually takes up room. I have 4 domains around my Sn. I have 3 bonding and 1 non-bonding. Okay, so 4 domains is tetrahedral, which means I am going to have to draw this 3D. I can't put this on a flat 2D surface. However, one of them is a lone pair though. So this is the electron domain shape. But what it's actually going to look like is this right here, since one is a lone pair. Okay, so electron domain, it's based off of tetrahedral, but because we can't see the lone pair, it's going to look like this. The molecule is going to look like this. All right, so let's draw this. Okay, so what I do, and it takes some practice drawing these in the beginning. Maybe have a small set of these yourself to look at while you're doing it. That might help. All right, so my Sn's in the middle, so I'm going to draw my Sn. My lone pair is going up, so I'm going to balloon up my lone pair. I have 1 Cl coming down this way that's also in the plane. So I'm just going to do a Cl like this and put my dots around it. Then I have 1 Cl coming out towards y'all. So remember, to do that, I kind of do a darkened triangular bond. And I put my dots. And then 1 Cl is going back towards the board, or in your case, towards your paper. So you draw that bond as a dashed line. And so see, this is what it would look like. So we have our Sn, our lone pair, our chlorine in the plane, our chlorine coming out towards y'all, and our chlorine going back towards the board. So electron domain geometry, well, I have 4 domains, 1, 2, 3, 4. So remember, that's based off of tetrahedral. So my electron domain geometry is tetrahedral. Remember, electron domain doesn't care if it's bonding or non-bonding. My molecular geometry, on the other hand, I can't actually see the lone pair. So what you have is you have a triangle with a pyramid on top. Okay, so see, this is the difference in what we just did. This is trigonal planar. See how you have the triangle, but it's all in the same plane. This is trigonal, because you see how you have your triangle, pyramidal, because see, it's not all in the same plane, it makes a pyramid. So my molecular shape is trigonal pyramidal. All right, see how fun this is? I love doing VSEPR theory. So hopefully you love it too. All right, so let's look at some more. And most of this video is going to be us looking at these. I'll just go ahead and tell you that. So that's why I'm saying you got to get good at Lewis dot structure, because otherwise I don't have time to do 4 million Lewis dot structures for these. All right, so our next one is SeCl2. So Se has 6 valence electrons, Cl has 7, but I'm going to multiply that by 2, so 14 plus 6 is 20. I'm going to bond them. Se is going to go in the middle. And for now, I'm going to assume it's linear. However, it might not be. It might be bent. I don't know. We'll see. So to make everybody stable, my Cl's each need 6 more electrons. And my Se has 4, so it needs 4 more electrons. So I check my total. I'm allowed 20, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. So I have 20, so I'm good to go there. So now I got to figure out, well, what is this thing going to look like? Okay, well remember, our electrons on our central atom are going to kind of balloon out. So if you look, I actually have 4 domains. So remember, 4 domains is going to take on a tetrahedral shape. However, this time, 2 of them are lone pairs. So if I find my model where I have 2 bonding and 2 non-bonding, this is what I end up with. Okay, so you can draw this all in the same plane as long as you just balloon out your lone pairs, because we're not interested in lone pairs being shown as coming out or going back as much as we are the atoms themselves. So what I need to do is I need to bend my CLs down and keep my lone pairs near the top. So what I would do to draw this is I would just do my SE, and see I'm going to do one of my CLs down, but keep the dots. Like, that's one of the things I found that y'all tend to do, is once you make it 3D, you feel like you don't have to put all the lone pairs on the outside atoms. You still need those on there, y'all. Alright, and then we have 2 lone pairs on top. So I just kind of do one like this and one like this to kind of show one's coming out, one's going back. So now let's talk geometry. So electron domain geometry, well, I have 4 domains. So remember, 4 domains is based on our tetrahedral. So anytime you have 4 domains, whether they're bonding or non-bonding, electron domain is tetrahedral. But for the molecular geometry, because some of them are lone pairs, I can't see those. So if you look, this isn't a straight line, it is bent. So my molecular geometry is actually bent. So see, once you get used to them, it's really not that bad. Like, this free theory is fun. Alright, so let's look at CO3 with a -2 charge. So I'm going to start by adding my valence. So C has 4, O has 6 times 3, and then I add 2 more for my charge. So in other words, I have 18 plus 2, which is 20, plus 4, which is 24. So I'm going to single bond everybody, carbon in the middle. And for right now, I'm just going to kind of draw it like a T. We'll find out the shape in a minute. Make everybody stable, so all my oxygens need 6 more. And again, y'all, if you're not good at Lewis dot structure yet, you don't want to be in this video. You need to get good at Lewis dot structure before you try to do VSEPR. Alright, and then carbon has 2, 4, 6, so it needs 2 more. Sorry, I almost said 10. I'm allowed 24, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. I have 2 extra electrons. I need 1 more bond. Uh-oh, I'm going to have resonance, because I could put that bond in 3 different places. So let me go ahead and adjust my electrons. So I'm just going to put it here first. I'll draw my resonance once I know what my 3D shape is going to be. There's no point in drawing resonance, y'all, before you pick the shape, because you don't want to then have to redraw all of them. Alright, so I adjust. So this oxygen has 2, 4, 6, 8, 10, so I'm going to remove 2. This carbon has 2, 4, 6, 8, 10, so I'm going to remove 2. And so this is what it's going to look like, because I'm allowed 24, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. I just realized I think it's possible I forgot to put brackets on my previous slide on that one that I just did. I'm sorry if I did that again, y'all. I'm just struggling to finish these videos at this point. I'm not going to forget this time. Alright, so this one we have resonance and we need brackets with our charge around it. Okay, so see how easy it is to forget stuff. Like, I'm super good at this stuff, and this is the second time I've forgotten something in one of these videos, but it's because I get going too fast, so just take your time and slow down. Alright, so I can see there are 3 domains. A double bond still counts as 1 electron domain. So 3 domains makes trigonal planar. So in other words, I can draw it all in the same plane, so I don't actually have to draw it 3D. But I do need to draw the 3 possible options where the double bond could be in any of the locations. Alright, so I'm just going to go through, and what I want you to notice is every time oxygen has a single bond, it has 6 lone electrons. Every time it has a double bond, it has 4. That'll help you keep up with, you know, how many you need. Alright, so first I'm going to draw it like this and put my extra electrons around my O for the double bond, it gets 4 electrons. For the single bond, it gets 6. I could also put it down here. So then I put my extra electrons, but I could also put the double bond over here. So then I put my extra electrons. Alright, and then the last step is I'm going to bracket the whole thing. Woo, sorry, that bracket got kind of crazy. And put my -2 charge. Okay, so you can see all of them now follow my trigonal planar shape. So my electron domain geometry, because there are 3 electron domains, is going to be trigonal planar. And remember, a double bond, y'all, still only counts as 1 domain. So it's going to be trigonal planar. Now notice my central atom doesn't have any lone pairs. If all the electron domains are bonding, then your molecular shape is the same as your electron domain shape. They're only different if you have lone pairs on your central atom. So my molecular shape is actually also trigonal planar. Okay, so as long as all your domains are bonding, these 2 shapes will be the same. It's the lone pairs that kind of throw everything off. Alright, so hopefully those weren't too bad for you. And so at this point, I still have plenty more to show you, but if you're feeling confident, you might want to start trying some on your own. Or there's still plenty more, so maybe watch me do a couple more and then start trying them on your own. Alright, so I'm going to do these 2, and then if you're not trying these on your own after this, you'll definitely want to start trying. Alright, so we have SF4. So let's do our Lewis dot structure. So S has 6 valence electrons. F has 7 times 4. So I have 28 plus 6, which is 34 electrons to work with. I'm going to single bond everybody by putting S in the middle. And I'm just going to put my F atoms just like that. Next step, I got to make everybody stable. All my F's right now have 2 from the bond, so they need 6 more. And then last, sulfur has 2, 4, 6, 8, so it's stable. So now let's check our total. I'm allowed 34, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. So remember, y'all, I don't have too many electrons to where I need to add an extra bond. I have too few. I'm supposed to have 34, I only have 32. So remember what I told you, some atoms can accommodate more than an octet. That's one of our exceptions to the octet rule. And sometimes it's sulfur, phosphorus, some of the halogens, and some of the noble gases. So I have no choice but to just give those extra electrons to sulfur, because I have to have 34. So those 2 electrons, though, are going to take up space. So sulfur, here, I'll balloon them out so you'll remember they're there. So sulfur actually has 1, 2, 3, 4, 5 electron domains. So in other words, it is based off of this right here. We have 5 electron domains. So I cannot draw this as a flat shape. The fluorines are not going to be at 90-degree angles from each other. I need to draw it like this, except one is a lone pair. So I will actually need to draw it like this. Now remember, when we're basing it off the 5-domain shape, the lone pair has to go on an equatorial position. So it can go here, here, or here. It cannot go on the axial positions because the axial positions have more repulsion because they're 90 degrees from every neighbor, whereas an equatorial position, it's at least 120 from some of its neighbors. Okay, so I'm going to set it up to look just like this. I'll even hold this up while I'm drawing it. Alright, so I'm going to draw my sulfur in the middle. I'm going to do 1F going up and put its dots. I'm going to do 1F going down and put its dots. I have 1F coming out towards y'all, so I'm going to do that darkened bond. I have 1F coming back towards the board, so I'm going to do the dashed line bond, and notice I'm putting all my electrons around my fluorines. Like I said, y'all like to leave that out. And then I have my lone pair coming towards me, so I just balloon out that lone pair. And see y'all, look at that. It's like perfect. My AP class did a good job on these. This is literally about the size that I always draw it in class. Alright, and so there you go. So that is my 3D Lewis dot structure. Okay, so let's fill out the shapes. So I have 1, 2, 3, 4, 5 domains. So that is based off of this right here, 5 domains. So remember, this is called trigonal because the center is a triangle, bipyramidal because there's a pyramid on top, there's a pyramid on bottom. Okay, so my domain shape, my electron domain shape is trigonal bipyramidal. Bi just means 2 pyramids. The molecular shape though, because one is a lone pair, I can't see this. So the molecular shape, this is the weirdest one for people to remember. It is seesaw. So molecular shape is seesaw. I mean, how do we have stuff like trigonal bipyramidal and then we got seesaw? You know, I mean, I guess people were staying up late trying to figure out molecular shapes one time and they were just giving up and like, oh gosh, just call it seesaw. I don't know what happened there. All right, so let's look at IF5. So first we'll add up our valence. So I has 7, F also has 7, and I'm going to multiply that by 5. So I end up with 42 valence electrons. Wow, 42. Hope my marker comes. I can already see it slowly dying from all these electron configurations. Lewis dot structures. Sorry. All right, so I'm going to bond everybody by putting I in the middle. And then I'm just going to kind of put my F's out right now. I can obviously tell it's going to have to be 3D since I clearly have 5 F's. So I'm going to have to draw it 3D at some point, but we need to see is it 5 domains or 6 before I can tell which shape to draw it. Okay, so all my F's, if you look, they each have 2, so they're all going to need 6 more electrons. Okay, so I'm just going to go ahead and fill those in real quick. Now I right now is already more than stable. It already has 2, 4, 6, 8, 10. But it has to have that many for all the F's to be bonded to it. So now let's check our total. So I'm allowed 42. I have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38, 40. Oh my gosh, I still don't even have enough. Okay, so again, when you have too few, you don't fix that with a bond. You fix too many with a bond. I have to give them to iodine. So let me balloon them out and give them to iodine. Because remember, if you have extra electrons, they're going to go on that central atom. Alright, so now let's figure out what this shape is. Okay, so if I look, I have 1, 2, 3, 4, 5, 6 domains. So in other words, that is based off of octahedral. And I know that might throw some of y'all off because octahedral makes you think 8, but yet there's 6 domains. It's because if we close this shape in, there would be 8 faces to the shape. But anyway, so this is what it's going to end up looking like. However, 1 is a lone pair. So I can't actually see it. So it's going to end up looking like this right here. So let me follow this shape. So I'm going to start with my I in the center. I'm going to do 1 F going up. I'm going to do my lone pair going down. And y'all, on this one, technically it doesn't matter where your lone pair is. Your lone pair could be up, it could be, pointing towards you, it could be anywhere. Then if you look, I have 2 F's, one on each side coming towards y'all. Okay, so I'm going to do an F over here pointing towards y'all. And an F over here pointing towards y'all. Alright, and then if you look, I also have 2 F's pointing back towards the board. So remember, to do that, I just do my dashed line bond. And I do one on this side. And so if you look, there is my 3D shape right there. Okay, so now we have to actually list what the shapes are. So the electron domain shape, I have 1, 2, 3, 4, 5, 6 domains. Bonding or non-bonding, 6 domains. So that is octahedral. Octahedral. However, because one of them is a lone pair, my shape for the molecular is not octahedral because I can't actually see this. So if you look, it is square. You see how the bottom makes a square? Square, pyramidal. Because see, there's a pyramid on there. So my molecular shape, because of that one lone pair, is square, pyramidal. Alright, so this is what a couple look like that have more than an octet. All right, so let's look at a few more. So definitely at this point, you're going to want to start pausing and trying these before I go over them. These are way easier when you watch someone else do them than when you try to do them yourself. So just make sure you can do this on your own. Okay, so again, pause it, try CLF3, and then let's look at it together. Okay, I'll assume you've done that at this point. So we have CLF3, by the way, this is an L, not CIF3. Cl, like chlorine, F3. So I'm going to add my valence, so Cl7. Fluorine is also 7 times 3, which is 21 plus 7, which is 28. I'm going to put my Cl in the middle, and for now, I'm just going to draw it like this, since I'm not really sure what the shape's going to be yet. I'll make everybody stable, so F has 2, so each F needs 6 more. And then chlorine has 2, 4, 6, so it needs 2 more. Last step is check my total. I have to have 28. I have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. So I have no choice but to give chlorine 2 more electrons. Or sorry, 2 more pairs of electrons, 4 electrons total. All right, so if you look, when we're coming up with our shape, this actually has 1, 2, 3, 4, 5 domains. So it is based on the trigonal bipyramidal. However, 2 of them are lone pairs. So this is the one I was missing yesterday. Here's my T-shaped one. 2 of them are lone pairs. They have to go on the equatorial position. See how they're on my equatorial position and not the axial position? They have to go on the equatorial position. But this shape is called T-shape. So many times we like to draw it in this orientation instead of this. However, you can draw it this way. That's fine. I'll show you both ways just in case. Okay, but I drew it like this. And if you look, mine already happens to be the perfect shape. Just like that. However, like I said, if you wanted to draw it in this orientation, because a lot of times in class I'll tend to focus on this orientation, because when you're first learning, it's easier to kind of just follow the same thing. So if you wanted to draw it like this, you would draw your Cl. You'll do 1F going up, 1F coming to the right, 1F going down. And then you have your lone pairs kind of ballooning out on this side. So see, you can draw it like that. You can draw it like this. I'm just glad I found the T-shaped molecule. All right, so now let's look at what our shapes are. So for electron domain shape, remember, bonding or non-bonding, I have 1, 2, 3, 4, 5. So that is my trigonal bipyramidal. Because remember, electron domain shape, it doesn't matter if they're bonding or non-bonding. So trigonal bipyramidal. So then for my molecular shape, remember, I can't see these, so we have T-shaped. See how it's a T? So it is called T-shaped. All right, so hopefully you got that one right. If not, pause it, try the next one, and then we'll look at that one together. All right, so we have ICl4. So this one is an I. So here, let me maybe do like this. This one is an I, and then Cl4, and then you have a -1 charge. All right, so my I has 7 valence electrons. My Cl also has 7 times 4. Whoop. And then my -1 means plus 1 more. So in other words, we have 28, 29, plus 7, which is 36. Okay, I'm going to bond everybody, so I is going to go in the middle. And I'm just going to start by drawing it as a flat plane. Okay, so all my Cl's, you can see, have 2 from the bond. So I'm going to give them 6 more each. And then I is already stable. It has 2, 4, 6, 8. So now I check my total. I have to have 36. I have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. So I have no choice but to give iodine those extra electrons. Okay, now of course I need brackets on this because it has a charge, but I'm going to put those on there when I fix it and make it 3D because it clearly ain't going to look like this thing. All right, so if you look, there's 6 domains, 1, 2, 3, 4, 5, 6. So it's going to be based on the octahedral. This is the one it'll be based on. But I can't see 2 pairs of them because 2 of them are lone pairs. So it's actually going to end up looking like this, okay, where I can't see the top and I can't see the bottom. All I can see is this middle portion. And so then we just draw it like this. Okay, so I'm going to take my eye, put it in the middle. I'm going to do one lone pair going up, one lone pair going down. And y'all, of course, there's other ways you can orient these, just like this. Just make sure you're drawing it 3D. That's really all I'm asking. All right, so 2 of my CLs are coming out towards y'all. So I'm going to do one on this side and one on this side. And then 2 of my CLs are pointing back into the board. So I do one going back on this side and one going back on this side. All right, and so if you look, looks perfect. However, last step is, of course, it has a charge. So I bracket it and put the charge. Okay, so there is my 3D structure for ICl4 negative. So now let's do our shapes. So the electron domain shape, there are 1, 2, 3, 4, 5, 6 domains. So that means it's based off of this, which is octahedral, 6 domains. However, since some are lone pairs, that means the molecular shape is going to be something different. All right, so my molecular shape is actually this. So if you look at it, see how it makes a square, but it's all in the same plane? This shape for a molecule is called square plane. All right, so hopefully you got one of those right. If not, it just takes practice. That's all it is. It takes a lot of practice to do these. First step is get really good at Lewis dot structure before you try to do anything 3D. Like if you can't get the original flat structure right, you're not going to be able to do the 3D one correctly or name the shape. So some of you may need to go back and practice in 8.2. All right, so the next thing we got to talk about are bond angles. So because a non-bonding pair experiences less nuclear attraction than bonding pairs, its electron domain is spread out more. So remember how I told you about that tantrumy toddler? If one parent is on both sides holding both hands of the toddler, they can't move around as much as if just one parent is holding on. And that's what it's like for a non-bonding pair. A bonding pair has the parent on both sides. A non-bonding pair is only attracted to one nucleus, so it takes up more room. So when you have a lone pair, the result is the electron domains for the non-bonding pairs exert greater repulsive forces on the other electron domains and tend to compress the bond angles. So normally in a tetrahedral type setup like this, our bond angles are about 109.5. Okay, so for this, it would normally be 109.5. However, once we have a lone pair, this lone pair takes up more room. So it kind of compresses these bonds to make them a little bit lower. And so then if you notice, this only has a bond angle of 107. So lone pairs will always take up more room and they'll compress the other bond angles. So you can notice the difference. So like a tetrahedral where there's no lone pairs, they're all 109. But once we have one lone pair, it compresses them to be 107. So it kind of bends them down a little bit. If we have 2 lone pairs, it compresses it even more to be 104.5. So a lot of times if they ask you what the bond angle is and you see lone pairs, you just put less than what it would normally be. So like for this one, you don't have to memorize necessarily 104.5. You would just put the bond angle is less than 109.5 because it will be compressed some. Multiple bonds do the same thing because of course there's more electrons in the same area. So multiple bonds contain a higher electron density, so they represent larger domains. So again, normally on a trigonal planar setup where we have 3 bonding domains, it should be about 120. But the double bond is going to take up more room. So these bonds are actually going to be more than 120 because what it's going to do is instead of it being perfect, it compresses these a little bit because it wants to push them away. Remember, all electrons repel one another. So it compresses them. So this bond ends up being less than 120 and these bonds end up being greater than 120. And like I said, y'all, you don't need to memorize these numbers. You need to know the less than or greater than. Like if this was if this was a single bond over here and everything was perfect, I would put all my angles at 120. But since this is a double bond, I know it's going to bend these towards each other. So I would put this bond as less than 120, and I would put both of these as greater than 120. Instead of trying to like pick the exact bonding. So let's go ahead and look at the sample exercise. So it says, eye drops used for dry eyes usually contain the water-soluble polymer called polyvinyl alcohol, which is based on the unstable organic molecule called vinyl alcohol, which is right here. Predict the approximate values for the HOC and the OCC bond angles. All right, so we have HOC, so in other words, we're looking right here. So we want to look at this bond angle. And then we have OCC, so that would be across this right here. Okay, so we're also looking at this bond angle. So when you're looking at bond angles in an entire molecule, just disregard the rest of the molecule for part of it. Okay, so like if I look right, so let me just disregard this part. So if I'm looking right here, I can just cover up all this. Let's just pretend like this is the whole molecule. I can see there are 4 domains. So even though you might want to say the bond angle is 180 because you see it drawn as a straight line, remember this is in 3D space. 4 domains cannot fit in 3D space. None of these are 180 degrees from one another. All right, so I have 2 bonding, 2 non-bonding. So what does that make? That makes bent. So even though it's drawn like this, in reality it would be bent. Now normally a tetrahedral structure has a bond angle of 109.5. However, some of them are lone pairs. So it's going to compress the bond angle even more. So for that one, I would put it is less than 109.5 degrees. Okay, it's less than 109.5 degrees. Just trying to look to see how much more we have with this. Oh well, this section just goes on forever. All right, well anyway, so next we have our OCC. So again, just pretend like none of the rest of this is kind of going on here. We have our O, we can kind of get rid of this part and get rid of this over here. So we have OCC. So here we have 3 bond angles. Right, 3 electron domains. So we're looking at a trigonal planar setup, which is like this. And so in trigonal planar, we have 120-degree bond angles. So we normally would have 120-degree bond angles here, but we do have a double bond. So our double bond is actually going to force the 2 single bonds a little closer. So if I was looking at this bond, it would actually be a little bit greater than 120 degrees. Okay, so you have to look at the fact that we have lone pairs on this one, which is going to kind of pinch the bonds together, and we have this double bond here, which is going to kind of squeeze the other 2 bonds together. So this one would actually be a little bit larger. So what happens is because this one's a double bond, these would come a little bit closer to each other in the bottom. So these would kind of squeeze a little closer. All right, so let's move on. Oh, this video is getting long. Hopefully this section is ending soon. All right, so it says predict the HCH and the CCC bond angles in the following molecule called propyne. All right, so we have HCH. So in other words, we're looking right here. Or you could look right here. I mean, either one works. HCH. All right, so again, I'm going to kind of cover up the rest of the molecule. So if you look, I have 4 domains. 4 domains makes tetrahedral. Tetrahedral has bond angles of 109.5. All my domains pretty much are the same type, single, single, single. So I can predict that I would pretty much have a 109.5 bond angle. Now, of course, you could argue, whoa, wait a minute, there's a triple bond up here. Wouldn't there be a little bit of squeezing? Well, it is a little further away from the triple bond, but there could be a little squeezing. So you could put less than 109.5 if you wanted, but mainly I would just leave 109.5 for that one. All right, then it says the CCC bond angles. So in other words, we're looking right here. Well, here we have 2 bonding domains. 2 domains, the only option for that is linear. So there's no guessing work here. A straight line is always 180 degrees. So that would be 180 degree bond angle right there. Okay, and so y'all, you don't need to think like, oh wait, but the triple bond is going to take up more room. We can't make this bond go any further away from it. If it does this, it's coming closer to this side. If it does this, it's coming closer to this side. This is literally the farthest away it can get on linear. All right, so, oh my gosh, we have finished. All right, so for section 8.3, the important thing is to know all your shapes, to know how to do electron domain shape and molecular shape. Make sure you can draw your Lewis dot structures correctly, and to know how to do bond angles based on the VSEPR shapes. All right, so hopefully you're getting this, and then just get prepared because section 8.4 is also super long.